Welcome to this video about compressors. So here we will talk about what actually is a compressor and why do we need a compressor. So there is one issue which often occurs in our mixes. So I draw this in a graph here quickly. So this is now a timeline, and this is basically the volume of someone, let's say someone singing. So we have a microphone, someone sings into that microphone, and then I'll draw here the volume of that person singing. So she might be singing pretty quiet at the beginning, she might raise her voice, come to a peak, go down a little bit, probably stay and go further down. So that could be a volume curve of a person singing. So what is the issue with this volume curve here? It could be that other instruments are at some points louder than the person singing. So it could be that at the start here, people cannot hear the person sing because she sings too quiet. It could also be that they cannot hear her sing at the end here because it's just too quiet. So what is happening when someone sings? The voice could sometimes stick out of the mix and sometimes like drown in the mix because other instruments or other voices are louder. So that's a big issue, and the question now is, how can we fix this issue such that the voice is always hearable in the mix? So actually what we want to achieve is we want to decrease this difference in volume. So this is the lowest volume, this is the highest volume, and this is the volume difference. So we basically want to decrease this volume difference such that we can make like quiet parts a little bit louder, so that all of the parts can be heard. So let's go into this whole compressor things. Actually now just already talked about the things. The dynamical range of an instrument or a voice can be made smaller or can be lowered, and this is how we can get more balanced levels. Yes, that's what I mentioned too. Quiet parts will stick out of the mix better, and the felt level of the mix can be raised in this way. So the volume doesn't always change but becomes much more constant, and the compressed signal can push through better compared to other signals. So basically we have much better control over the signals if we use compression. Always be aware here that if the signal is compressed too much, so we can make this range too small basically, and if the range is too small, then the instrument doesn't sound natural anymore. It will then sound like it hits a wall basically, because we lowered that range way too much. So I will now explain you 2 steps how equalizers work. What equalizers basically do in the first step is we take down the loud parts. So the loud parts where the volume is high, we make it a little bit more quiet, and then in a second step we raise the volume at every point in time back again. So let me explain this to you in detail on this drawing here. So what we do, let me pick blue for this one. What we do in a first step is we decide for a certain volume, for a certain, we call it threshold. So let's pick this volume here. We decide for a certain volume threshold, and what we basically do is tell the compressor, whenever the volume is above this line, above this threshold, turn down the volume a certain amount. So I draw here the result of this first step. So the signal volume will be exactly the same until we reach the threshold. It will not be changed, but now we reach the threshold, so it will be turned down. So it could look somehow like this. So it will be something like this. And when we pass the threshold again at the end here, we again have the exactly same signal. We don't further turn it down. So as soon as we pass the threshold, the signal is turned down at every point in time. So the question now is, how much do we turn it down? How much should we lower the volume of the signal? And the answer for this is ratio. So there is a parameter called ratio. In some mixers it's also called range. And the goal of this ratio or range parameter is to define by what extent the signal should be turned down. So normally it's like a ratio. It's not, we don't turn it down by a certain amount of dB, but we turn it down by how much it exceeds the threshold. So if it exceeds the threshold by, let's say, 9 dBs, and we have a ratio of 1 to 3, we turn it down 1/3. So we turn it down 3 dBs. That's what the ratio says. So it's always the difference in volume starting at the threshold to the current volume. And the ratio basically defines which fraction of that volume difference we turn down. So that was step number 1. We use threshold, we use ratio to turn down the signal. And now we come to step number 2, which is we lift the signal back again. So what we can observe now, we could already lower the range of the volume. So if we look at that volume difference, it's now already smaller. So this is the loudest, the most quiet volume is still the same. So this difference, it did shrink now. But we actually want everything to be loud. We actually, our original goal was to make quiet parts louder, right? So at the moment, loud parts are more quiet, so we now have to do the second step to get basically everything a little bit louder again. So what we do in the second step is basically increase or turn up the volume at every point in time, no matter what the threshold is. So at every point in time we turn up the volume such that we end up with something like this. No, that was that is not 100% correct here now. Let me see if I can do that again. So we go up here. Basically I just draw the blue curve again. With just a higher volume. It should, this is now much better, huh? So we basically turn the volume up at every point in time, and we see now the volume difference is like that. It still stayed the same as after step 1, but now the quiet parts are louder. So here the quiet parts, they became louder, and the parts which were basically above the threshold before, we turn them up again now. But as they were decreased before, they will basically end up at the same point as they were before, so it doesn't really change the volume there. And this is how we achieve our goal to turn quiet frequencies louder. This parameter to turn the frequency, to turn the volume up again, is called makeup gain. At some consoles, it's also called output gain. So that's the basic functionality of a compressor. So I will now go through these different parameters again, through threshold, through ratio, through makeup gain, just in a bit of a more formal way. There's also a few other parameters we have to take into account. There's a few more things you can do. So on the next slide, here you can see the signal graph I drew before again, just a bit more formal. So here in blue we have the input level, like the original level, which is like going this way here. And now we can see the dashed line here is again the threshold. And as soon as the signal passes the threshold, we start to do gain reduction. We turn down the volume. So it is turned down whenever the signal is higher than the threshold. So starting here and ending here. And here we already see that there is two additional parameters we can set. There is an attack time and then there is a release time. So an attack time defines how long it takes until the volume is reduced by the predefined ratio. So the attack time is the time it takes until, and this is the red signal, this is the output level, what the compressor does to the signal, how long it takes until the volume is reduced to the output level defined by the ratio. So that's the attack time. It will then stay like that, and then when the signal drops again to below the threshold, of course the output signal drops the same amount, but then we have another parameter which is called the release time. And the release time basically defines how long it takes after the input signal dropped below the threshold until the compression stops, so until the gain reduction of the signal stops. So you see, at first we are a little bit below the signal even though we are below the threshold, and then it basically compression stops until we are at the original signal again. So that was basically almost all of the parameters available in a compressor. So let me now show you a few pictures where I explain you again the different parameters, and I also want to give you some advice how you can use the compressor in good ways. So first, threshold again. Threshold is the parameter which you use to set the point of the volume at which compression starts. So whenever the signal level is above that point, we will start reducing the volume of the signal. So practical advice here, always start with a threshold very high, like actually always put it at 0 dB, and then turn down -6, -12, -24 until compression starts. So you can find more easily the point where you have a good amount of compression. If the sound is over the threshold always, you set the threshold too low. What does that mean? So if your sound from the microphone is always, like if the volume is always above the threshold, you will always do compression, right? No matter how loud or how, like no matter the volume of the sound. And that doesn't really make sense because you will basically just be always making the sound more quiet, which you don't want to. You just want to make loud parts more quiet and then turn the whole thing up again. So make sure you just compress loud parts and not all of the parts in the of the sound. Then ratio. Here I decided to give a little question to you so maybe you can stop the video at this point to calculate the output level. So the question here is, we have an input level of -10 dB. So the input volume is -10 dB, and we set the threshold to -20 dB. So the input level is at -10, threshold is at -20. So the input level is 10 dB above the threshold, and we set the ratio 2 to 1. So what does that mean now? Can you calculate the final output volume of the compressed signal? Just try that now. So the solution to this question is minus 15 dB. How do we get to this minus 15 dB? So first thing we have to recognize is that the threshold is minus 20, the input level minus 10. So the difference is 10 dB. And then we have to look at the ratio. The ratio is 2 to 1. So that means we lower the signal, or we can basically divide the difference by 2. So we take it down half. And if we do that, we end up at 5 dB reduction. So we are at minus 10, we do 5 dB reduction to end up at minus 15 dB output level. Then there is these two parameters, attack and release, I talked before. And this graph shows it pretty nicely how it works. So these bars here basically represent the input level. And we have here like two different cases. So in the left picture here, we see pretty fast attack time and fast release times. And in the right image here, we see slow attack times and slow release times. So what happens if we do a fast attack, which means like almost 0 milliseconds and also almost 0 milliseconds release time. So if the attack is fast, the signal passes the threshold line, which is the red line here. And as soon as it passes the line, the signal is reduced. And then at a certain point, the signal drops below the threshold again, and immediately after the signal goes below the threshold, we stop the compressing. So the volume differences will be quite harsh, happening quite fast, like either lowering the signal, like compressing the signal, or not compressing the signal. So compression will act very fast. Whereas when we do slow attacks and slow release, it means that the signal goes over the threshold at this point, but we wait with the compression a little while. So the signal is already over the threshold for a certain time, but just after a while we start compression, and we do compression until the signal drops below the threshold again at this point, and then we do compression for a little longer until we then stop compression, even though the signal was below the threshold for a certain amount of time already. So here we get much smoother compression curves. It doesn't happen so fast. So we start compression after a certain time, compression hits, but then when it goes below, we still keep on doing a little compression and then slowly remove the compression. So these two graphs just should give you a little bit of intuition on how this works. Probably also stop the video here and check out these two graphs in detail to really understand how the compression is done with attack and release time. It's actually really just delays. It's 2 times you set on when to start compression and when to end compression, always connected to the signal level compared to the threshold parameter. So there is one important thing to know about the attack time. The attack time is very important for drums. Drums do have so-called transients, and this is basically a little peak in signal after the volume actually raises from the drum sound itself. So when you hit the drum, you will have a very short signal peak first, and then the real sound of the stick hitting the drum. And this transient is really important for the characteristic of the drum. And this transient you don't want to compress. So what we normally do is we set a compression attack time to approximately 60 to 70 milliseconds. That's the time it takes the transient to go through. And just then we start compressing. So that's a very good application of the attack time. I normally try to lower the attack time to almost 0 for voices because we don't have the transients there. And the release time, I almost always set it to 100 milliseconds or above. just so that the changes in compression or no compression are not too fast. I want the compressor to work smoothly, so if the signal goes below the threshold again, that the compression stops very slowly, so that we have a smooth signal curve and not just drop the signal down because we don't, or basically push it up again because we don't do compression suddenly anymore. So always try to use some release, but don't do it too long, because especially for drums, if the drums is playing fast beats and you do too long of a release time, you will not get out of compression anymore. So make sure you put that release time into a good range there. Then there is another parameter I have not been talking about so far. This is the knee. So the knee basically just defines the smoothness of the change from no compression to compression. So at the point where we pass the threshold, we can basically decide how fast we want to, how smooth the compression should start. So it defines the overlay of compressed and not compressed signal. The change shouldn't be too hard, as it may sound unnatural. So for practice, this means the knee should look round, not edgy. So when we look at a compressor, it normally looks somehow like that. Let me pick black here. So you have, so this is if the signal is not compressed. This is like minus 60 dB, minus 50, minus 30, minus, I don't know, 24, 12, minus 6, and the same thing here. So this is no compressed signal at all, and when you add the compression, you basically decide here where the threshold is, so at what volume you start to compress. Basically how much you take the upper curve down is the ratio. So if you turn it all the way down, the ratio will be like 100 to 1 or infinity to 1. Then it would be basically a limiter. And then basically this point here is the knee. So if you make this a little rounder like this, then this means you turned the knee up, so the compression when the signal passes the threshold will be happening more smooth. So I always push I always turn the knee up a little bit, so to get a little bit of a smoother compression. And of course, the last thing, very important, the output gain. You should always turn up the compressed signal again, such that the quiet parts become a little louder. Of course, you could in theory also do this with the channel fader, but that's actually the goal is actually to do it with the output gain, to always keep the gain structure nicely. So if you compress your signal by, let's say, 6 dB max, you could set your output gain or makeup gain 6 dBs to 6 dBs plus. So that's basically all about compression. It's quite a little bit of a difficult topic, so probably watch this video a few times to really understand what is happening when we do compression. Thanks for watching.